All right, today we're diving deep into a question that is right at the heart of quantum mechanics. How in the world do you predict the future when you're dealing with the smallest things in the universe?
So, how do you do it? Picture a whole crowd of quantum particles. You know everything about them right now. But what about a second from now? Or a minute? How can you possibly predict what they're all going to do together? This isn't like tracking billiard balls on a table. This is the quantum realm, and it plays by a completely different and way weirder set of rules.
So where do we even start? Well, the first big step, the real trick, is you have to stop thinking about them as a bunch of individuals. If you want to understand the crowd, you need one single, powerful way to describe every single particle, all at the same time. You need one rule to govern them all.
And that one rule has a name: the multi-particle wave function. I know it sounds like a mouthful, right? But the idea behind it is actually pretty beautiful. It's just a single piece of math that acts like a master file, bundling up all the info: where they are, how they're moving, their spin, the whole shebang for every single particle in the system.
Okay, now don't let the symbols on this slide freak you out. Just look at the big picture here. You see all those little G's? Each one is like a profile for an individual particle, and the equation's job is to scoop them all up and combine them into that one big size symbol on the left. That's it. That is our master description, a perfect snapshot of the entire quantum crowd.
But, and you knew there was a but coming, right? There's a catch, a really big one. To make any of this work, to even write that clean equation, physicists have to start with a major simplification. They have to pretend the particles are completely ignoring each other. No pushing, no pulling, no interacting at all. It's the only way to build the foundation before things get really complicated.
Now, even in this simplified little universe where nobody's interacting, it's not a total free-for-all. There are still some very strict rules. And for a certain class of particles called fermions, think electrons, there's one social rule they absolutely have to follow. It's a fundamental law of their quantum society.
And that rule is super simple to remember. Two's a crowd. Seriously. For identical fermions, you just can't have two of them in the exact same state at the exact same time. They're just a little too antisocial for that.
And this isn't just a guideline. It is a hard-coded property of the universe. If you even try to describe a situation where two identical fermions occupy the same state, the math literally breaks. The wave function, that master description we talked about, it just cancels itself out and becomes zero. Poof! It's the universe's way of saying, nope, not allowed. Okay, so let's recap. We have a way to describe our non-interacting crowd, and we know they have to follow certain rules. So how do we actually use this to predict the future? Well, this is where a concept called scattering comes into play. And really, it's just a physicist's way of talking about the ultimate before and after picture.
The central question they're trying to answer is this: if you have a perfect description of a system of particles way back in the remote past, that's before they get anywhere near each other, can you then calculate what they're all going to be doing in the far future, long after they've flown past one another?
And this slide just lays it all out. On the left, that's our before shot. We've got our system of particles, each with its own profile, those G functions. Then on the right, that's our after shot. Same particles, but now they have totally new profiles. We'll call them the F functions. The million-dollar question is, how do you get from G to F?
Now here's the crucial quantum twist. You're not looking for one single guaranteed outcome. That's not how this works. The whole key to quantum prediction isn't about saying what will happen. It's about calculating the probability of all the different things that could happen. And to do that, you need a very special tool.
And that tool is called the scattering amplitude. Basically, it's a number. And this number tells you the exact probability that your group of particles, starting in that initial G state, will end up in one particular final F state. You can run this for every possible future to create essentially a map of the odds.
And this, right here, is the engine that calculates those odds. That S stands for the scattering amplitude. But don't think of it as just a dry equation. Think of it as a probability machine. It's the bridge connecting the past to the future. You feed in what you know about the before. You feed in one possible after, and it spits out a number, the odds of that future coming true.
So let's just break it down into 3 simple steps. First, you tell the machine everything about the particle's past states, the G functions. Second, you propose one hypothetical future, the F functions. And then third, the machine crunches the numbers and tells you the exact probability of that specific transformation happening. You do this over and over for all the possible futures, and you just predicted the quantum crowd.
Okay, I know what you might be thinking.
Non-interacting particles, remote pasts, far futures, this all sounds incredibly abstract. So why does any of it matter? Well, it matters because this seemingly simple model is actually the bedrock for some of the most important physics in the entire world.
You know, when scientists at the Large Hadron Collider smash particles together and predict what will come out, they are using these exact principles. The computer or phone you're watching this on, understanding how electrons behave in its semiconductor chips depends on this. It's a cornerstone of quantum electrodynamics, which, I'm not exaggerating, is one of the most astonishingly successful and precise theories in the entire history of science. So we've built this incredibly powerful tool for predicting the future of a quantum crowd. But we did it by making that one huge simplification. We assumed they don't interact. And that leaves us with one final fascinating question. What happens when we turn the interactions back on? What happens when we take this simple model and throw it into the beautifully messy, complex reality of our universe? Well, that is where the next chapter of the story begins.